So we will see now identity hash map and weak hash map. Okay, and in map we have key value pairs, correct? So what can be the usages? We have zip code, cities. Zip codes can be keys and cities can be the values. We have error code description, managers and employee, between the relation between managers and employee. Classes and student can be an example also. So these can be the usages. These can be the usages of map, correct? Now we will see what is identity hash map. Okay. So here in identity hash map, what we will see is, before anything else, I want to show you a single difference which I have shown you before also. Okay, there is a difference between equal to and dot equals to and dot equals to. I have explained this process. I have explained this difference before too. Okay, let me take this simple example. Integer I1 equals to new integer 10. Fine. We do not have to use this. Integer I2 equals to new integer 20. So just for the difference I am showing you. Fine. And s out I1 equal to I2. So what do you think? What will be the answer? Will it be true or will it be false? Okay. And in this case also I have explained you this, therefore I am asking, what do you think, what will be the answer in these two cases? What will return true and which will return me a false? Fine. So just think a little bit. So I1 is pointing to a different object and I2 is pointing to a completely different object. Okay, since these two are pointing to different objects, what we are saying is I1 equal to I2, the equal to operator just matches their references which are totally different. They are not same in this case because I1 is referencing to something else and I2 is referencing to a different location. Fine. So this will return me a false. What dot equals does it matches the container. That is 10 and 10, so it will return me a true. So this is the difference between these two, dot equal to and dot equals to, correct? So what equal to does, it will compare these. Okay, as you can see, the answer is false and true. So it will simply compare the reference variables, and the value in reference variable is completely different. Okay, so this is the difference between equal to and dot equals to. Okay, fine. So dot equals to will actually compare the container values, that is 10 and 10, but equal to will compare the reference values. Okay, so therefore they are false and this is true because I1 is pointing to a different object, that is I1 is referencing to a different object and I2 is referencing to a different object. So just keep this difference in mind. Okay, so let's now see identity hash map. So let's see a program, a simple small program. So I will use hash map only. First hash map. Okay, hash map m equals to new hash map. Fine. And then what I will do, I will write the same program again. Integer I1 equals to new integer 10 and integer I2 equals to new integer 10. Fine. Now I will simply use m dot put. I am adding some values. M dot put I1 comma I1 is now my key and I can write Goku. Okay, so some of you will know the name Goku. Then m dot put, and in this case I will use I2 and here I will write Gohan. So if you know Goku, you will know Gohan also. Fine. So let me print now. So s out m. So what will happen is, now let me tell, I have shown you what put does. If these two values are same, if the key values are same, it will overwrite. It will simply overwrite. First it will add I1 and Goku, no issue. Then when it is going to add I2 and Gohan, it will see if these two values are same or not. If I1 and I2 are same, then it will simply overwrite Goku with Gohan. Correct? I have told you this. So in case of hash map, what it does, it calls dot equals function. In this case, it calls dot equals function. Okay, it will use dot equals function, not equal to. So if he uses dot equals function, I1 and I2 are actually same. Why? Because 10 and 10, they are the values. I have shown you that in dot equals true was the answer. So these are same. So if I now run this, what will happen? I will get the output as this I1 and I2 are same, and the Goku will be replaced by Gohan. So 10 equals to Gohan is my answer. Fine. So I think you understood this. Okay, fine. So if you want more clarity, just s out of m. What will happen is, first I1 and Gohan, that is 10 and Goku, will be my answer. As you can see here, 10 and Goku is my answer. Then when I again write m dot put I2 and Gohan, what hash map does, it simply calls dot equals function, and dot equals function will return me a true for I1 and I2 case, correct? So which I've shown you earlier. So 10 and Gohan, so Gohan will replace Goku, as I've shown you in the previous code also. When if I use put method for same key values, it will override the previous value. So this was in the case of hash map. What happens in the case of identity hash map is completely different. Identity hash map calls equal to function. What it calls equal to function. So this is the only difference between hash map and identity hash map, and there is no other difference. All the functions are same, and also there is many things same in identity hash map and in hash map. Fine. So why it is showing error here? Put is by mistake what I have done, I have used the same name as identity hash map. We should not use the same name. So if I change the name of my class, now it will tell me that import this one, the actual one. So when I import this, the actual one, now when I import the actual one, now I have changed the name, and I have removed public from it, so now there will be no error. So this identity hash map also have these same functions, m.put and m.put. There the functions are exactly same. The only difference is when I call I1 and I2, so I1 and I2 will now call equal to, not dot equals to. And in the case of equal to, they are not actually same. They are completely different. They are not now same, but they are different. Fine. So as you can see here, now what I will get Goku and Gohan as a different value, but the key values are same. Now you can see in identity hash map my key values can be same. Okay, for the same key value, that is 10, I can have two different values, Goku and Gohan. So if by any logic you want this thing in your code, so you can have it. Okay, so this was identity hash map, and the only difference between identity hash map and my normal hash map is the comparing of the key values. The identity hash map uses equal to, and my hash map simply uses dot equals to. There is no other difference. So now we have completed with our identity hash map, and let's move on to the weak hash map. So before moving to weak hash map, you should know the concept of garbage collector. So you should already know the concept of garbage collection, but I will just explain you. If I have an object, okay, and this object is referenced by some variable, for example m is referencing this object, so there is not an issue, and we have our garbage collector standing here. Okay, so he's at on, garbage collector is at on, he can kill any object which is not referenced from anywhere. Fine. So because this object will then become a garbage, okay, and he will come and he will kill it. Fine. So if I remove this, so now object becomes alone, and the garbage collector will see it, and he will see, yes, now I can kill it, now I can eat it. Okay, so the garbage collector will come and eat the object. Fine. So this is how this is just an analogy, okay, how a garbage collector kills an object. Fine. So this is required in weak hash map. So now why the name weak hash map and why the name normal hash map? So yes, you are thinking correct. Weak hash map is actually weak, and the normal hash map is actually strong. Yes, this is the case. I will prove it. Just give me 5 minutes. So what happens is, if I have my key value pairs, correct? So just now in the example, I have used an object to point to a key, correct? I have used a reference variable I1. So I have an hash map. So my value was 10 and Goku, correct? Just now, and also 10 and Gohan. Fine. So this value came from an object, and this object was referenced by I1. Okay, this object was referenced by I1, and this value also came from an object, and this was referenced by I2. Okay, so one was referenced by I1 and another one was referenced by I2, correct? So what will happen if I write this now, I1 equal to null, fine. So this will go, and the object now will become, just in case, just I have explained to this object that is not referenced by anything, so the garbage collector will now come. So the garbage collector came, it sees this and it came, nothing is referencing you, so I'm going to kill you. So when he says I'm going to kill you, what will happen? Our big boss is here, that is hash map. What hash map will do, he will come and he will save the object, because this is a strong personality, and it is stronger than my garbage collector. Fine. What garbage collector will do, garbage collector will go to our JVM is the biggest one. So what JVM will say to garbage collector, that hash map is strong, if you want to delete an object of a map, go to a weak hash map, What weak hash map does is, weak hash map is not that strong, what he will do, he will just leave, and you can kill the object, So the name is actually really weak hash map. Okay, so this was not just a joke, it is weak because it cannot protect its own objects. It cannot protect its own objects. Hash map can protect the objects, but the weak map hash map cannot protect its object. Okay, let's now see this whole scenario in a code. Fine. So this is the code I have written for weak hash map. What I am doing, I am declaring a hash map m equals to new hash map and a temp class which I have given here. So there is no use of this temp class. Just I wanted a reference variable. So temp t equals to new temp t, nothing else. Okay. Now what I do, I wrote m dot put t comma Luffy. So now I have a hash map. Fine, simple. And here what I will have t is my reference variable, some value of that reference variable, and Luffy. Okay, so here there is some value. I will print the value, don't issue, there is no issue. Now what will come here is, if I do t equals to null, which I have done in the next step, t equals to null, as you can see I have done in the next step, and in the next step I have called my garbage collector. In this step I have called my garbage collector. So garbage collector, what will see, or t became nil, so I can just now kill that object. He will think that, but what we will have here is simply that hash map will protect it. Hash map will protect it. Fine. So let's now run it. If after this garbage collector I am doing system.out.println and just run this class, sorry. So after this system.gc, that is garbage collector, if I run this, see, I will get the value temp, there is some value of this t and equals to Luffy. Fine. So it is not deleted. It is not deleted. Why? Because our hash map has protected. Our hash map is protected it. Fine. So these two lines, that is system.gc and thread.sleep. Thread we will say in multi-threading, but the system.gc is used here to call the garbage collector. Fine. So we are calling the garbage collector. Now what we will do, we will change the hash map to weak hash map. Fine. So we have changed it. Now let's see. Now the problem is the weak hash map will not protect the object. Weak hash map will never protect the object. Now what will happen? My object will be deleted. As soon as the garbage collection will come, he will kill the object and my value will be gone. As you can see, there is nothing inside my map now. So weak hash map is actually weak, and a normal hash map is a strong one. Therefore the name was weak hash map. I hope you understood what is the difference between a normal hash map and a weak hash map. This is the only difference between these two. All the functions are same, all the constructors are same, but the only difference is this is actually weak. It cannot protect it on its own object, but the strong hash map, that is a normal hash map, is actually strong. Fine. So this was our hash map. So now we have completed with our weak hash map also. Our identity hash map is also over. Linked hash map and hash map is completely over. Now we will see sorted map. So you have seen sorted set. It is exactly same. I am telling you, it is exactly same. Then we will see navigable map. We have also seen navigable set. The functions are also same, only the name is different. And this is tree map. We have seen tree set. This is also same. Okay, I will just explain everything now. Just for sorted map, navigable map, and the tree map. Okay, let's do this. So for sorted map, let's begin. Now let's see what is sorted set. Okay, sorry, sorted map. Just keep in mind what was sorted set. It is clearly same. Okay, sorry, it is very same. So it is a child interface of map. Okay, we know that. If we want to represent a group of individual objects as key value pairs according to some sorting order of keys. So there was in sorted set, if we want to represent a group of individual objects as single entity and in some sorting order. So it is same, just here it is sorting order of keys, and instead of single entity we have a key value pair. There is nothing difference in these two. Okay, now sorting is based on key but not based on value, because we have two things here, key and value. So the sorting is based on key. Okay, now let's see the methods of sorted map. So it is an interface. So take care, the methods will not be implemented, just defined here. It will be implemented by tree map. Okay, so the first one is, it is same here. There we had the first method, here we have a first key method. So it returns the first lowest key currently possible in the map. So the currently possible, so if this is my map, so the first lowest key that is currently possible in this map is 101. Correct? The 101 is the first key. Next we have the next method, the last key. So the last highest key. So last is 136. So my answer will be for the second method is 136. So I know you remember these things. In sorted set also we have done this exact thing. So the next one is head map. So returns a view of the portion of the map whose keys are strictly less than the given key. So if my given key, for example, is 107, if my given key is 107, so all the values that are less than 107, strictly less than 107, so my answer will be 101, 103 and 104, not including 107. Okay, so what will be the answers? Just not the keys but the values also. So I am just adding keys, just take care of that. 101 equals to A, 136 equals to F, so 101A, 103B, 104C. So these will be the answers. Okay, now the next one is tail map. So it will return a value of portion of this map whose key are greater than or equal to, since it is not strictly greater, and if I pass 107 again, now my answer will be 107 equal to D, because it is not strictly greater, it is greater than and equal to. Because of that equal to, I will also get 107 as my output. So 107, 125 equals to E, 136 equals to F. Correct? So the next one is submap. So between the two keys, from key and to key. Okay, so from key is inclusive and to key is not inclusive. So if I pass 103 to 125, if I pass the two keys, that is 103 to 125, so 103 will be inclusive and 105 will be exclusive, and the answer will be 103 in curly braces equals to B, 104 equals to C, 107 equals to D. Okay, and these answers will also be in curly braces. So we will do this, actually not we, you will do this when you code for tree map. Okay, so we have code for tree set, this is exactly same. So when you code, when you try for tree map, these methods you can implement directly there. Okay, one method is comparator. Now I have already explained you what is the use of comparator. So comparator returns the sorting order, and if we are using a natural sorting order, which in case we are using, this is a natural sorting order, the default natural sorting order, that is for numbers ascending, and for string or characters alphabetical, then it will return me a null. But if I'm using my own sorting order, that is customized sorting order, which I have shown you during tree set, there what we can do, the comparator will return the method that we are using. Fine, it will not return me a null. It will only return me a null in case we are using natural sorting order. Fine. Next is navigable map interface. So it is a child interface of sorted map. Child interface of sorted map. It's very simple. It is exactly same as navigable set interface. So we have the methods, and the methods are also same. There we have a lower method, here we have a lower key method. There we had a floor method, here we have a floor key method. We had a ceiling method, here also we have a ceiling key method, and a higher key method, there also we had a higher method. So these methods are exactly same. What you can do, you can just simply write a code, okay, for tree map. What you can do, just write a code for tree map, and in that code of tree map, what you will do these all things you have to do. This is, take it as a homework. Just write a code for tree map, and in that, simply what you have to do, you have to simply use all these functions which I have just explained in sorted map and navigable map. Okay, now next is tree map. So it is an implementation class of sorted map and navigable interface. Fine, sorted map interface and navigable map interface. So all the methods which I have just shown you are actually implemented in tree map, and you can use these methods by declaring a reference variable of tree map. We have done this in tree set also, so you have to write that code. Now it is underlying data structure is red black tree, so you will learn about red black tree in the data structures. Fine. Now duplicates are not allowed for keys, but values they are allowed. So we have seen this. Insertion order is not preserved, but all the elements will be inserted according to some sorting order. We have also seen these points. The points are also same in these two. So for DNSO, what is DNSO? My default natural sorting order, keys should be homogeneous and comparable. We have seen what is homogeneous, we have seen what is comparable, we have seen the difference between comparable and comparator also. There is no need for me to explain all these points again. For customized sorting order, keys can be homogeneous or heterogeneous and may or may not be comparable. Okay, I have told you this one also. Okay, so use of comparable, comparator, I have done this. Now constructors of tree map, they're exactly same as tree set. We have the first constructor, that what it creates a tree map object where elements will be inserted in default natural sorting order. Next, we use our own sorting order using the comparator. I have shown you this example in tree set. Next is if you want to convert from a map to the tree map, and next is if you want to convert a sorted map to a tree map or a normal map to a tree map. Okay, these are the constructors. The constructors are also same. Fine. So now what we have done is we have completed our map interface 2. Okay, so what we have done, we have completed our sorted interface. So now what we have done, we have completed the collection interface, and in this video we have completed the map interface too. But what you have to do is you have to write this code for tree map. The code is exactly same as tree set. You have to use these functions. Fine, just write for practice. Okay, everything is same. Okay, only the difference is between the single entity and a key value pair. Here we use key value pair. Okay, the usages, I have also told the usages of map. Okay, so I have completed the collection interface now. This was, sorry, a collection framework now. So okay, so this was obviously a very long topic, so we have seen so many things. Okay, so thank you. Just write these codes which I am telling you to write and revise the collection interface thoroughly. Fine, thank you.